Hi and welcome to the third video in the series The Geometric Approach to the GCD. In this video we will complete the block matrix method for solving linear Diophantine equations and extend it to the sets of integers where no pair is coprime but the overall GCD is 1. If you are unfamiliar with the block matrix method, I recommend watching the earlier videos in this series. You can find the playlist in the description. In the previous videos, we explored how the Euclidean algorithm for finding the GCD of A and B can be expressed as a linear transformation. This transformation maps a vector DD to AB, and the rows of the inverse provide solution to the Diophantine equation AU plus BB is equal to D. We then introduced a block matrix construction to extend this method to linear Diophantine equations with n variables. However, this approach required the first two elements of the set to be coprime. But what happens if that condition is not met? Let's consider three integers a1, a2, and a3 where their GCD is equal to 1. Suppose the GCD of A1 and A2 is greater than 1, while the GCD of A1 and A3 and A2 and A3 are both 1. Using the block matrix method, the transformation T of A1 and A2 and A3 will map 1, 1, 1 not to A1, A2, A3, but to A1 over D, A2 over D, and A3, where D is GCD of A1 and A2. However, since there are coprime pairs in the set, we can construct additional matrices to resolve this and eventually map 1, 1, 1 to A1, A2, and A3. The inverse transformation then provides the solution to the associated linear Diophantine equation. But what if there are no coprime pairs in the set, even when the overall GCD is 1? Consider the set 35, 55, and 77 with the GCD equal to 1. Here all GCDs are greater than 1. And the goal is to solve the equation 35x plus 55y plus 77z is equal to 1. Using the Euclidean algorithm, we first construct the unimodular matrix T of 35, 55. Then we build a block matrix using this. This matrix will map the vector 1, 1, 1 to 7, 11, 77, where 7 is 35 over 5 and 11 is 55 over 5. To correct this, we find a vector 5, 5q that this matrix maps to 35, 55, 77. And we can determine q through simple calculation. We then reapplied the block matrix method to find a new unimodular matrix U mapping 1, 1, 1 to 5, 5, 5 minus 303. Just note that here, since we are looking for the matrix of 5 minus 303, we can use a matrix n to negate the second element. And this will not disturb the matrix, since n is a special kind of matrix whose inverse is equal to himself. So we will use this matrix to build a new unimodular matrix U, which maps vector 1, 1, 1 to 5, 5 minus 303. The product of T and U gives a transformation M that maps 111 to 35, 55, 77. The inverse of M provides solution XYZ to the original Diophantine equation. To generate infinite solution, we express M as its inverse symbolically, like this. Substituting and simplifying reveals a particular solution XYZ in the last row, with additional solution derived by adding integer multiples of certain values to this solution, as we can see here. So the last row is this particular solution, and the first and the second row are general solution with M and N being integers. To generalize, consider sets like 35, 55, 77 with pairwise GCD greater than 1, but an overall GCD of 1. To build such sets, we start with a set of pairwise coprime elements and create a new set A by grouping product of distinct primes into subsets of 3. This guarantees GCD of A to be 1, while maintaining pairwise GCD greater than 1. Now the goal is to find the unimodular matrix mapping the vector of 1s to the vector A. And we know that the GCD of A1 and A2 is greater than 1. So we start building the unimodular matrix T of A1 and A2, and then we use it to build the block matrix using another unimodular matrix B. As we saw, this matrix won't map the vector of 1s to the vector A. So we define an intermediate vector V, which the transformation T will map it to the vector A. The elements of V are related to D, and the inverse of the unimodular matrix B, as we can see here. Once the elements of V are determined, we want to reapply the block matrix method to find the unimodular matrix U, such that U will map the vector of 1s to the vector V. For this, we have to find two elements within the elements of V, such that the GCD of Vi and Vj is equal to 1. Then we build the unimodular matrix of Vi and Vj, and since we want to build our block matrix properly, we use a permutation matrix P to put the two elements Vi and Vj at the first and second place of the vector V. Then we build our block matrix UP, and we apply the inverse of the P to put the rows at the right place. Doing this, the U will map the vector of 1s to V. Then we multiply T and U to obtain the overall transformation matrix M, which maps the vector of 1s to the A, and the rows of the inverse matrix are the solution to the associated differential equation of the elements of A. Let's do a quick example. First, we want to build a set with pairwise GCD greater than 1, but the overall GCD equal to 1. For this, we build a set of numbers which are pairwise coprime. Then, by grouping them, we build our set A with elements that are pairwise not coprime, while the overall GCD is equal to 1. And we want to build a matrix to solve the associated linear Diophantine equation to this set of numbers. For this, we start by building the unimodular matrix of the two first elements, 105 and 210. Then we use it to build our block matrix and define our intermediate matrix vector V such that T will map V to A. Then we find two elements within the elements of V such that they are coprime. And we build the unimodular matrix of these two elements, here being 15 and minus 15, 497. Then we build our second unimodular matrix, mapping the vector of 1s to the vector V. And the product of T and U will map the vector of 1s to the vector A. Here we can see one example of this matrix M, since we can by tuning the elements of the block C, we can obtain other elements, and also by using another matrix for B. And here we can see that the inverse of this element will map the vector A back to the vector of 1s. This means that the rows of this inverted matrix is the solution to the linear Diophantine equation associated to the set A. The block matrix method is now complete, allowing us to construct a unimodular matrix for any set of integers and use it to find particular solution to the associated Diophantine equation. However, linear Diophantine equations have general solution, which we will explore in the next part. Thank you for watching. I look forward to your comments and feedback. Bye.